So just to get started, here's a comic from XKCD where the people are talking to each other. One says, I used to think correlation applied causation. Then I took a statistics class. Now I don't. The other person says, it sounds like the class helped. And the first guy says, well, maybe. So why is this funny? Because if you understand causal inference, you understand that it's actually difficult to estimate the treatment effect of something like taking a statistics class. In order to know whether the statistics class helped, we would have to know counterfactually, would you have figured out that correlation and causality are not the same thing without the statistics class? And of course, you might have figured it out by reading the newspaper or following a discussion on Twitter or from some other class, not your statistics class. And so in order to conclude that the statistics class helped you actually understand a concept, you need to have a theory about the counterfactual. And so the fact that this guy says maybe the statistics class helped is sort of reflecting that, in fact, he understood that causal inference is actually hard. And really the core concept of causal inference is understanding counterfactuals. What would have happened in the absence of a treatment, or what would happen if there are alternative treatments. So just to get some motivation and kind of fit this into a broader set of concerns in machine learning and causal inference, in the last few years, we've been seeing a lot more attention to additional properties desired of machine learning models beyond the ability to just improve goodness of fit. And we've been seeing this desire in part because we've seen that when you can learn about machine learning in a classroom, but when you go to try to put it into practice in a real application in a firm or for a government or for a social impact application, that actually just training in the machine learning model is the easy part. And actually making it sure that it's going to be accepted and be effective in context is the hard part. So, and actually in most cases, getting a slightly better mean squared error is just not important at all relative to other considerations. And so I won't be able to have time to go into all the reasons you would like these other considerations, but things that people talk about are interpretability, stability or robustness of the models. So for example, if you have a machine learning model that tries to predict creditworthiness, whether you'll repay a loan, that might not be very stable or robust if there's a global recession following COVID-19. Transferability, will something that I estimate in one context work well in another context? Are algorithms fair? Do they discriminate? And there's generally a recognition that a lot of AI that we've seen in the last 10 years is pattern recognition, and it doesn't really have the human-like qualities that we would associate with intelligence. For example, can it make reasonable decisions in circumstances that it's never seen before? And so, although in principle, all of this can be solved with a causal inference framework, although I'm going to illustrate that the fact that it could be solved doesn't mean that it will be solved, and most often it won't be solved. But in principle, a causal inference framework addresses all of these concerns, because the goal of estimating parameters of a model in a causal inference framework is to learn a model of how the world works. If you would like to estimate what would happen if I change some treatment, that is a model of how the world works. I want to know what would happen if I change a treatment. That's basically changing the underlying data generating process. That's no longer pattern recognition. It might be that in the past, every time a user logged into a website, they got a certain recommendation and then they made clicks. If I change what they see when they log onto the website, in order to make a prediction about that, I actually have to have a model of how the world works, because the joint distribution of user actions and treatments that we saw in the past will change in the future. And that change in the joint distribution is something that can only be modeled by understanding how an underlying model of how people make choices, for example. So one thing that's very difficult is actually just trying to discuss these concepts without formal language. And so one thing that I think almost all people who work in causal inference agree is that you actually need to have some definitions. You need some mathematics. You can write that mathematics in diagrams. You can write that mathematics in equations, but you do need some formal structure. And I found that very expert machine learning scholars can get themselves confused without the benefit of a formal logic. So that's whichever, there's many alternative formal structures you could use. Whichever one you choose, though, it's very important to have one so that you can actually define what you're talking about. Now, an ideal causal model, by definition, is stable and interpretable. So in applied fields that have been doing empirical work for decades, we spend a lot of time talking about things like internal validity and external validity. Internal validity is about whether you've actually learned something in the context you're studying, and external validity is about how well it generalizes. So I might study changing the minimum wage in one state at one point in time, and then we will try to discuss whether that result would be generalizable to a different state in a different point in time. And if we've done it well, we've actually understood how the world works, we'll know where it generalizes and where it doesn't. But a lot of that is about domain knowledge and understanding assumptions and arguing whether those assumptions hold, rather than something that directly comes out of the data. Another aspect, which I won't have much time to talk about further today, but is a very hot topic, is fairness and discrimination. And I'll just highlight that a lot of the issues that come up there also relate to correlation versus causation. There's actually a lot of deep philosophical issues there, but we can ask, for example, if I took the resume and changed the Russian name to a Chinese name, how would that affect your ability to get a job in either Russia or China or America? And so we can think about the causal impact of your resume being identified with a particular ethnicity. Those types of issues can be put into a causal inference framework, and that can actually help you sort out what you mean by fairness. And there's lots of different meanings of fairness, but one version might be that if we'd had the same information and the same skill set, but I just changed your ethnicity in terms of the interview process, would that change your probability of getting hired? In practice, even though a formal framework and ideally would allow you to deal with all of these issues, the challenges in causality actually are typically due to an inability to find a good data set that satisfies the relevant assumptions that allows you to do the exercises you want to do. So the challenges are not about finding new models. There sometimes, occasionally, very rarely, people come up with new ideas in causal inference, but this is something that people have been working on for decades. So a lot of the core ideas are already determined, especially the ones that are most useful in practice. So in practice, if you're an applied researcher, the biggest challenge is actually finding a data set and a setting that allows you to answer an interesting question. And so that's what most of the effort goes into in applied literatures and empirical data-driven literatures in causal inference. There's a few kind of famous people who spend a lot of time talking about the philosophy, but actually most of the hard work and hours and papers are about good applications. And so in particular, if you want to understand the answer to kind of what if questions, what if I change something, you need to have data that enables you to learn enough about the way the world works to answer those questions. And in economics, we often call that quasi-experimental variation. So in the past, if you ran a randomized experiment, that makes things easiest of all, still not perfectly easy, but easier. But if in the past you didn't run a random experiment, you need to find something that happened in the past that's as good as if you ran an experiment. And that's what's going to allow you to do counterfactual inference. And that's where a lot of the creativity has come in to figure out how can I identify a setting that has this type of variation. We often, though, end up in a situation where there's something unobserved to the analyst that basically makes it almost impossible or even provably impossible to answer your question. And a lot of this literature has theorems that say, even if you had an infinitely large data set, you still can't answer your question if there's certain types of unobservables. And so there's a theory that has nothing to do with having good neural nets. It's like, no matter if you have the best neural net in the world, there's a theorem that says I still couldn't answer my counterfactual question unless I have the right kind of data. Another big challenge is the analyst's lack of knowledge about the model, that you just might not understand exactly how your data was generated, and that can also get in the way. If you're trying to do personalization, which is one of my big areas of study, you also often have problems with insufficient data. And even if you have data from a search engine or something where you have billions of observations, a lot of times that's still not enough to answer interesting questions about personalized treatments. So I'll also come back to talk about that. Today, I'm not going to talk about personalization, and you have another speaker in the summer school who's going to be focusing on that, but I'll just point out that is one of my big research interests as well. So to tie causal inference a little more into things you might be more familiar with if you're experts in machine learning and artificial intelligence, we can relate artificial intelligence to counterfactual estimation. Artificial intelligence that is trying to actively learn and make choices. So artificial intelligence that has, a player playing a video game or playing a chess game, or a player who's trying a robot that's trying to climb over a wall in reinforcement learning. In all of those examples, there's sort of a statistician inside the AI that is trying to estimate what would happen if I moved my piece to this other position. What would happen if I moved my leg in a certain way if I'm a robot. So at its core, artificial intelligence of that sort is trying to select among alternative choices, and it has to have an explicit or implicit model of payoffs from those alternatives. If it wants to do that, it's going to have to learn from past data. The initial stages of learning have limited data, but inside the AI, there's a statistician doing counterfactual reasoning. Now, historically, a lot of times the AI algorithms didn't actually think much about the statistics literature that focused on how to efficiently learn in an environment where you're trying to do counterfactual reasoning. In more recent years, there's been more cross-fertilization across disciplines, and ideas from the statistics literature on estimation, efficient estimation in causal settings has started to come into bandits and reinforcement learning, and indeed has led to improvements. So that's just an idea of where there is some fertile ground to be reached. Once you understand that reinforcement learning is really about counterfactual inference, you realize that all of the research that's been done over many decades about how to do that well could be relevant here. So just to kind of see an example of that, let's think about a contextual bandit. So in a contextual bandit, there's some context, we'll call that X. And we're trying to learn which arm is better, arm 1 or arm 2. And so on the left here, we can see what data would look like from an initial batch of bandit data. In the initial batch, where you don't know anything about the arms, you would randomly assign the individuals who arrive to either arm 1 or arm 2 because you don't know which arm is better. And so the red dots, which are assigned to arm 2, are going to be equally distributed between low and high X's, just as the blue dots are that are assigned to arm 1. If I then try to fit a model, a simple machine learning model, to try to estimate what is the relationship between the arm rewards and X, my estimate of mu1 and mu2, these red and blue lines, those are the estimates of the arm rewards as a function of X, those will reflect accurately the underlying structure, because the initial data was randomly assigned. So these are just two simple supervised machine learning problems. They may be noisy without a lot of data, but we should generally get the shape right. But then after the first batch of data, we actually learn that for high X, it looks like arm 2 is better. And for low X, it looks like arm 1 is better. So in the next batch of data, we gather a lot of these dark blue dots, as in the second batch of data. For when you get a low X, you pull arm 1 because that looks like it's better. When you get a high X, you pull arm 2, and that because it looks like arm 2 is better. So now when you look at the new data set you have to learn what's the relationship between X and outcomes, we're going to, if we fit a simple model through there, those models may actually have bias. And in particular, if we try to fit a line or a simple curve through the purple dots, it's going to be flatter than the true relationship, because we've gathered a lot of data in a region where the purple curve is flat. The blue curve, it's kind of dark blue purple. Sorry, I keep switching. It's flat, and I haven't gathered as much data in the region where it has curvature. And the same for the arm 2 with the red curves. So the dotted lines show our estimated models after we've collected a second batch of data. And now those estimated relationships are actually biased. And if I think counterfactually, what would happen if for a low value of X, I pulled arm 2, I would look at the dotted line and I would actually overestimate how good arm 2 is. And the reason I would overestimate is because I'm extrapolating from the data that I have for high values of X. I use the high values of X to learn about the relationship between X and the reward. I extrapolate to the low values of X and I make a mistake. And so I would get, if I wanted to say, what's the treatment effect? What's the benefit of using arm 2 as opposed to arm 1 for a low value of X? I might underestimate that benefit because basically all I know about arm 2 is learned from higher values of X where the reward to arm 2 is higher. So this is, even though I've generated the data myself and I understand the data generating process, if I'm naive and I don't actually take into account the way that I generated the data, I will end up with bad inferences and my bandit will make mistakes and it won't get to the right answers as quickly as it could. And also if afterwards I said, how much is it worth it to pay? Suppose one of these arms is more expensive than the other. How much is it worth it to pay for that arm? I would also get incorrect inferences about that. So this is just an example where a bandit generates data, but not incorporating the statistician inside the bandit makes the performance worse. And so I have a paper in AAAI where we demonstrate that with further simulations. And we show how using techniques from causal inference can help to eliminate these problems. So more broadly, if I want to now define the literature that I work in and that a lot of the applied social scientists and biostatisticians work in, we call it things like program evaluation and treatment effect estimation. That's one branch of the literature. I'll come back and talk about another branch in a few minutes. And so this branch answers questions like, what was the impact of the policy? Suppose the government raised the minimum wage. Suppose the government put in a program to retrain workers, say, displaced by COVID-19. What if a school changed the maximum size of classes? I want to measure quantitatively the impact of that. And so I just want to be clear here. We already have a theory. We know and we believe that these policies have some kind of causal effect. The question is how big and even in what direction? Because when you raise the minimum wage, that could be good or bad for workers. It depends on how big the increase is. So we want to measure the magnitude, how big is the effect, and what is the sign. We're not trying to discover whether minimum wages cause employment or whether employment causes minimum wages. That's like causal discovery. We're saying here, we know, we already understand that the problem is that the government changes the minimum wage and we want to estimate the effect. Okay? Other types of questions we might look at is, did the advertising campaign work? What was the return on investment from an advertising campaign? That's a very common question that firms need to answer in digital marketing. And they want to understand, if I turned off the advertising, how many sales could I make? Interestingly, in the time of COVID-19, a lot of companies stopped their advertising and they learned that they had previously overestimated the benefits of advertising, that when they stopped advertising, they didn't lose as many sales as they had thought that they would. Other types of things that are very active right now are get out the vote campaigns. So the United States has a big election coming up, and we have people who are measuring the impact of sending advertisements on Facebook, using chatbots, using telephone calls, and so on to try to get people to vote. We also want to do things like, well, who should be eligible for a program? So if I have millions of unemployed workers, for whom would a retraining program or a resume building program be most beneficial for getting them to work? There might be people who are just difficult to help, and other people for whom the programs are very beneficial. So the general approach that we take to these problems is we first think about a research design using domain knowledge and detective work that credibly answers the question. And there, we're not thinking first about how big the data set is. We're asking, is there a situation where if I had lots and lots of data, I could credibly answer my question? So an example might be that, the government had a lottery that they used to allocate people to training programs. And they used the lottery we could see all the people who applied to the lottery, and then we compare the people who were chosen to be in the program to the people who were not. And if I learned that such a lottery had taken place, I would get very excited as an empirical person, because I would know, oh, great, here's a case where there was basically a randomized experiment, and I actually have a good way to learn about the impact. Once I have figured out the design, I need to formally state my assumptions and then provide supplementary analysis to defend them. So I would need to, first of all, say, well, gosh, I can't see what the impact of the training program is for everybody. I can only estimate it for the people who applied for the lottery. But within the type of people who did apply for the lottery, I can estimate a causal effect of the training program by comparing those who won the lottery and were admitted to the training program and those who were not. I might have to I might use data to show that actually the lottery was really correctly run and there wasn't some corruption. Maybe the person assigning things said they ran a lottery, but they really didn't. So I would want to use data to show that indeed it looks like the people who got the training program are similar to the people who did not. Finally, I need to think about an estimation approach that does a good job. And that's where the machine learning techniques come in. I need to think about, is it a neural net? Is it a random forest? And I also have to think about how I regularize in order to make sure that I get unbiased estimates of my causal effect. So generally, when we think about these, we break things into the estimand. So first of all, what do I want to estimate? Do I want to estimate the average effect of a training program? Or do I want to estimate heterogeneous effects? So if I wanted to do an optimal treatment assignment policy, I want to learn for whom is the program good and for whom is it not. Then I want to go through a set of designs. And it turns out that there are some designs which are most common to find in practice that actually work pretty well. So here's a list of these designs, and now I'm going to go through and show you what some of those designs look like just through examples. It's easier to explain these through examples than just theoretically. So the first example is called a regression discontinuity design. And so these are often used for things like access to educational programs. So just as an example, in Kenya, in Africa, there was a study that tried to understand how important is it to go to a better quality school. And that's a difficult causal question because it's often the case that people with richer parents and more motivated parents put their kids into better quality schools. So even if we just tried to compare students from good quality schools to students from bad quality schools, we wouldn't know whether it was the school itself or instead whether it was just the parents of the kids that were good at figuring out what the good schools were and getting their kids into those schools. So that's one reason that there's a lot of debate about the impact of school quality, even in settings where we actually have a lot of data about students. So you can imagine that if all ways in the past, the way that kids got into high quality schools was through their parents' effort, even if I had millions of observations of students and schools, I still wouldn't know the difference between the impact of the school and the impact of the parents. Okay? So that's the challenge we're trying to solve. And the way that we solve this challenge is that we, in many cases, is we look at a regression discontinuity design. So in many cases, to get into a good school, there may be some kind of test that you take. And so if you have a test score that's just above the boundary, then you get into the school. And if you have a test score that's just below the boundary, you don't get into the school. Another example that's also commonly used with schools is schools are sometimes allocated by location. So people who live within, 2 kilometers of the school have a preference to get into that school. There, again, we would try to compare people who lived close to the 2 kilometer boundary, the people just inside the boundary who are more likely to get into the school, to the people just outside the boundary who are less likely to get in. And so here's a picture of what a nice result looks like for regression discontinuity designs. If we look at this cutoff, the people just above the cutoff for getting into the good schools have higher graduation rates than the students who are just below the cutoff and go to a lower quality school. And so this gap, the gap between the outcomes for the good students and the bad students near the boundary, is our estimate of the causal effect. Now you can see from the data why this is actually a hard problem, because you can also see on the x-axis are your scores, the scores that helped you get admitted. And we see that there is a positive relationship between having a good score on the x-axis and having a good outcome on the y-axis. And so if we weren't careful, it would be hard to determine whether it's just that good students get into good schools and have good outcomes, or whether there's actually a causal effect of the school. But it's the fact that there's a break point near the boundary that allows us to draw causal effects. There's a substantial empirical literature that gets into how do I estimate right at that boundary, that gap, because the thing you worry about is if you're not careful and you just apply a simple supervised learning model, if you try to estimate what's happening right at the boundary, say let's take the people to the left of the boundary, and I try to just take only data to the left of the boundary and estimate what's happening at the boundary. Well, if you look at that, if the people who were above the boundary had actually been assigned to the better school, you would have more data about the bad schools for people to the right of the boundary. But you're censoring your data right at the boundary. And that tends to, all else equal, pull estimates down because we're building a model for people who on average have underlying scores less than 0. So all your data is less than 0, but you're trying to do an estimate right at 0. And so one of the kinds of techniques that happen is that when you're estimating a model like this and you're trying to use it for regression discontinuity, you tend to overweight the observations that are very close to the boundary to make sure you get good estimates right at the boundary. And then you're also very careful about running a model to extrapolate that's going to perform well at extrapolating near the boundary. So the way you do the weighting, as well as the way you do the model evaluation, is tightly tailored to the fact that your goal is to come up with an estimate right at 0. And I don't really care how I do at -30 or -20. I really want to get a good estimate right at 0. And I understand the pitfalls of trying to estimate on a boundary. Okay, so a lot of the machine learning here is about solving a very tailored goal, estimating at a boundary. This is a very commonly used technique in the applied literature. And again, the schools is probably the most common application, but generally any type of government program that has this kind of threshold is useful. Now, if you ever consult for a tech firm that can run a lot of experiments or a government, one thing you might notice is that the thing that made this problem hard was that there was nobody with higher scores that actually got the good school, and there was nobody with scores below 0 that got the bad schools. One thing that's been suggested as a way, if your goal is to actually not just assign students today, but also learn for the future, is what you might have done instead is, well, let's take all the students from -5 to +5 and hold a lottery among them. That would be almost the same thing. It would take away this hard threshold, and it would allow us to learn better in the future, because then I could have a set of students with actually equivalent test scores who randomly got into the good school. Now, students might complain, oh my gosh, you shouldn't randomize, this is so important. But on the other hand, you might argue that it's unfair to students that just missing one point makes such a big difference in their life. So, taking a set of people close to the threshold and randomizing might actually in some ways be more fair, and also might allow us to learn more from the future. So Roberto was asking, regarding generating data, our personal preferences might cause bias. So I guess one way to think about personal preferences here is that in this setting, there was a score that was letting you in. But in general, if you look at who's going to which school, people chose to go to those schools. Either their parents chose for them or the students chose. And so the people who are willing to drive the farthest and spend the most time lobbying and spend the most time learning, getting their kids into a good school, are going to, in general, also be the people who are most likely to succeed later, relative to people who don't have the time, knowledge, or ability to do that. And so generally, economists think about people making choices. They think about everything that happens to a person as actually being them responding to their own preferences, abilities, and options. So we think about anything you would see, whether you were in a training program, which school you went to, which drugs you took. Our first assumption should be that those were choices made by individuals to maximize their utility. And if you think that's the way the world works, then you're going to be very careful trying to draw inferences about treatment effects when the treatments were actually responding to things about the people that we don't observe. So the whole problem this is solving here by looking at the test scores close to the boundary is that these were all very similar people in terms of their characteristics. And it was actually, so it is valid to compare the people just above the boundary to just below the boundary, because the people just below the boundary would have gone to that better school if they had just had one more point on the test. So the assumption is that plus or minus 1 point on the test does not have a big effect on outcomes. And of course, we can measure the effect of the points on the test on outcomes away from the boundary within either the group that went to the good school or the group that went to the bad school. But our goal is to estimate this gap. And so another way to frame what the goal of the empirical exercise is to estimate counterfactually for these people who were just below zero, what would have happened if they were up in the good quality school group, and for the people just above zero, what would have happened if they had been reassigned to the bad quality school. That's the formal goal of the counterfactual analysis. So another type of very closely related design is a design of just panel data, longitudinal data, data where you watch over time. And there you make the assumption that there's whatever the underlying characteristics are of the people or the places, those are constant over time. So back in the 90s, I worked on the adoption of information technology. And there was something called E911, which was basically caller ID when you call emergency services. And so it used to be that if you called an ambulance on the phone, you would have to spend a minute or two giving your address and giving directions to your house. The E911 technology basically gave that call center access to maps, so that when you called from a landline, an old-fashioned landline phone, they would immediately see your address, and that would be displayed on a map. And that would help the ambulance get there, 1 to 2 minutes faster. And if you have a heart attack, 1 to 2 minutes can make a big difference. And so here the data set we had were counties, administrative districts in the state of Pennsylvania. And over the course of a couple of years, they each adopted this technology at different times. And so what we argue is that we can compare a county just before they got the technology to just after they got the technology and and understand the causal effect. Now, it might also be the case that having the technology requires some learning, and so the benefits might increase over time. And so the simplest empirical model you can use here is you just create longitudinal data where every quarter for every county in every quarter I have an observation. So here there's 18 quarters of data, and we're going to look at all the counties and run a simple regression maybe a logistic regression if the output is binary, a simple logistic regression where I estimate quarter effects because hospital technology and medical technology changes over time, and county effects because some counties are different than others in terms of their hospitals and so on. And then on top of that, I have indicators for whether or not you have the technology and how many quarters have you had it. And then here I'm plotting the coefficients where I see that after the enhanced 911 adoption, the health of the patients gets better and better over time. And here, the outcome is basically an outcome about predicted mortality. And so it's showing that each quarter, roughly in the quarters after you adopt the new technology, the mortality rates are falling for each quarter. And of course, it's a bit noisy there as well. So this type of panel data regression has been used a lot in economics and also in medical studies. And the idea is just that here in this case, I put in indicator variables or factor variables for counties. I can estimate what's different about the county. I can also, by putting in factor variables for time periods, estimate what's different about the time periods. And then having taken out those effects, I can isolate the treatment effect. Now, those were done usually using simple regressions with factor variables. And in some of my recent research, I've tried to bring in matrix factorization techniques to this problem in order to better estimate, not just assume that there's a linear functional form, but to allow for a latent factor structure. And I won't have time to talk about it today, but I think you had another speaker who's talking about variational inference. I actually show how to use variational inference to estimate the parameters of that model using machine learning techniques. So one thing you can do is you could go back to some of these settings that people in the past analyzed using simple linear models where they assumed there was a single time effect for each quarter, a single dummy variable for each county, and revisit those using matrix factorization techniques. Another type of model is we call structural estimation or generative models. And again, those are some of the ones that I've used variational techniques for. Generally, these structural models are used to do counterfactuals in a setting where I haven't observed exactly that situation happen in the past. So I'm trying to understand what would happen if two firms merged, or what would happen if you raised a price to a price I've never seen before. And in those situations, I need additional assumptions. So if we think, and another type of question we might want to answer is what's the impact on welfare or profits of participants in alternative counterfactual regimes? And this type of analysis has also been used for several decades, and it's commonly used in merger analysis. So I want to understand, what if I allowed, Facebook and Instagram to merge? Or what if, what if I allowed, then what would happen to the quality of the product? It's typically been used in simpler industries, though, like there's two different companies that are both selling the same product, and I want to understand what would happen if they merge. In these types of settings, what I want to do is estimate consumer preferences. And if I understand how consumers feel, both about prices and about the characteristics of the products, then I can understand how those consumers would respond if one of the products went away or if the prices changed. And I'm basically using what I call revealed preference to uncover preference parameters, and then I try to use those to generalize to unseen situations. Just an example of where I use this historically, and I use this in analysis of sponsored search auctions. In that case, we think about advertisers placing a bid. And we let Q of B be how many clicks a firm gets as a function of its bid. So if they're bidding on Google or they're bidding on some other search engine, they place a higher bid. And if they place a higher bid, they'll be ranked higher on the page and they'll get more clicks. So the bidder's profit per search is Q of B, that's their profit as a function of bid, times their value per click minus their bid per click. If I just solve the first order condition for this, I can write the equation as V equals B plus this, the ratio of the quantity of clicks to the derivative of the quantity. This is just from first order condition for maximization. The reason we write it this way is that on the left-hand side is the bidder value. That's something I don't observe. While on the right-hand side are quantities that I could possibly observe from the data. For example, if I use a tool that bidders use to try to estimate clicks, I can see counterfactually what would happen if I raised the bid higher or if I lowered the bid. And from that, I can figure out this function Q of B, and I can also figure out its derivative. If I assume that the bidder was actually maximizing profits, then if I know the bid that they chose, and I have estimates of how the quantity of clicks changes with the bid, I can infer what value would have made that bid optimal. So it's like sort of like inverse reinforcement learning. This is something that economists have done for many decades in empirical analysis. This idea that you assume that someone's maximizing, and then you try to figure out what value would have rationalized their bid. If you can estimate those values, then I can do counterfactual analysis, because if I knew what all the advertisers' values were, I can imagine a new game that they're playing. I could imagine changing reserve prices or changing eligibility criteria, and then I could recompute a new equilibrium. And so that's called structural analysis in economics, but it's very closely related to inverse reinforcement learning in computer science. I would say that there's many, many, many more applications of these concepts in economics than there are in computer science. But typically, where the economists have gone wrong is that they've often made very strong functional form assumptions, and they've also really limited their models because we didn't have good computational techniques. Back in the 80s and 90s, when we would try to estimate these models, we just didn't know how to estimate them very well. Now, with modern machine learning techniques, we're much better at trying to estimate these types of models with flexible functional forms. And we're also able to accommodate much larger state spaces as long as we have sufficient data. So the ideas have actually been around for a long time. There's not like a brand new conceptual idea, but what's really new is the implementation and the ability to take it to large data sets. So I just want to contrast that. You're going to hear from other speakers about causal discovery or learning the causal graph. That is really almost orthogonal to everything I've talked about today. So today, I've imagined that you as the analyst, you understand there's a bidder in the auction. You understand that there's a relationship between bids and clicks. Your goal is to estimate values and use that to answer a question for the search engine, like what happens if I change reserve prices? While causal discovery would just say, oh, I'm going to take a big data set and I want to understand, I don't know whether values cause bids or bids cause values. I don't know, I don't really understand what's going on here, and I'm going to use the data to try to understand what's going on. Economists tend to think that, gosh, even if you did understand, these problems are so hard, I'm going to look at like the one very small part of a causal graph, and I'm going to work really hard to do a convincing job estimating that part, even with a lot of domain knowledge. And to economists, it feels almost impossible to imagine just taking a bunch of data and figuring out a causal structure, given how hard it is to actually estimate causal effects once you do believe that you know the graph. But I think that's really just a difference of the types of applications that we work in, and that often economists are working in settings where almost everything is determined by the system, and actually it's really hard to isolate the causal effect of even one variable. Well, if you're in a biological system, or if you're trying to think about a system, an engineering system where there's underlying physical relationships, then, and there's lots and lots of variables, these other types of applications of saying, I want to understand the underlying structure would be more applicable. At least that's the way I think about it. So, so let me stop here, and I'll take questions now about the specific things I talk about today, and then I'd be happy in our fireside chat to come back and discuss more, bigger philosophical issues as well. So let me pause here and take questions, and you can put questions into the chat as a first preference, but also if you want to unmute and speak, that's okay too. give a minute for people to type into the chat. So how do Bayesian graphs fit into this framework? So when going back to these kind of applications of where we have, you know, this type of advertiser profit model, for example, in one of my papers, I use classical techniques, and the other, another paper, I use Bayesian techniques. And there you can imagine putting a prior over the advertiser values. And I might even have a hierarchical model where I use, say, what industry the bidder is in to help me understand, to set a better prior for the advertisers in that area. And then for some bidders, I might only see them place 1 or 2 bids, and so I'd be fairly uncertain about what their values are. While other bidders, I see them make, you know, I see lots of changes in their environment, and I see them responding to that with different bids. And so I might have a much tighter posterior about the bidder values. So I would write down my generative model, like the equations I've written here. I would layer on top of that priors about the advertiser values, and then update them using Bayesian techniques. In my work with David Bly on estimating consumer preferences in shopping data, we also put a prior over consumer preferences, and we then use variational Bayes to try to estimate consumer preferences. So we have lots of consumers and lots of products, and we're trying to estimate the consumer preferences. But similar to these equations, we assume that the consumers are maximizing utility. But I would say that you don't have to estimate these using Bayesian techniques. Bayesian techniques are kind of nice because they very nicely accommodate the idea that there's some people for whom we don't have a lot of good information and others that do. And they also nicely accommodate the very high dimensional space of latent parameters if you have lots and lots of individuals that you're modeling. But you don't have to use Bayesian techniques. Where I think Bayesian really connects, though, is that I think Bayesians actually are very similar, whether they're in machine or they're in economics or they're in marketing or somewhere else. Bayesians generally believe that you need to write down a model of how the data is generated. And I think that is a very important component of doing good causal inference. So sometimes, sometimes you write down a model of how the data is generated, and then you use maximum likelihood to estimate the parameters. Sometimes I write down a model how the data is generated, and I use Bayesian techniques. But in either case, you want to write down the model. And I think that's one reason, like David Bly and I kind of connected and understood each other well at the beginning. He was used to writing down these Bayesian models, and it was very intuitive to him to think about writing down the data generating process. I would say that one difference, though, is that a lot of times a Bayesian framework that's non-causal doesn't think as hard about confounding and the idea that there might be unobservables that are, that make it hard to draw inferences. And the causal inference literature typically will emphasize theorems that focus on a specific estimand, like the causal effect, or maybe your sensitivity to price, or the causal effect of a treatment. And something that a Bayesian wouldn't always do is to really kind of distinguish what's the difference between just a parameter of a distribution that well describes this data generating process and a economic or policy question we want to answer. So I might be able to have a parameter that well describes a stochastic process, but that parameter might not be useful to answer a question about what if I change the stochastic process by intervening in the environment. Other questions? So in these examples, we had access to historical data. How does one handle a situation where there's no historical data, new products or customers? Yeah, so these can be important challenges. I think in general, in practice, we do cluster them. So that's one example where the Bayesian framework would be really nice, because I can, I have some kind of hierarchical prior, and if I see something about the new product or the new customer, then I can come up with, I can update using their characteristics. And that's going to be important for personalization. But another kind of situation, though, if we're thinking about a new product, is that if I have characteristics of the products, I can watch the people respond and see how they feel about different products. So if in the past there were lots and lots of products, and those products have different characteristics, and in addition, sometimes products enter, sometimes products exit. And furthermore, in the past, prices also changed. If all of that type of stuff changed in the past, then I can start to learn, how do you feel about characteristics of the products? And if I understand that, in principle, I could predict what happens if a new good enters. And that's one example where actually having a more structured interpretation is really important. Somebody's going to come to you and say, well, what if we introduce a new version of our product that has better quality? And if you're the data scientist answering that question, just a neural net on the past without any structure on it may not help you very much. But a lot of the techniques that have been used in economics and marketing were specifically designed to exactly answer those questions. So the question was, is it still possible to learn causal relationships if there's not a situation such as in the regression discontinuity design? In general, there are theorems, impossibility theorems. So if you either have to assume that whatever treatment you're interested in, whether it's a price or a training program, you either have to assume that that was as good as randomly assigned in the past, or you have to assume that you've observed all the characteristics of people that related to treatment assignment in the past. But if you don't make some assumption, you cannot draw inferences about causality. So, and that is a pretty deep idea. I used to get into big arguments with machine learning people at the search engine who just kind of argued, well, if I just had a good enough neural net, or if I just had enough data, then I would be able to. And you have, it can be really helpful in those cases to actually write down the mathematics and prove the theorems that show you that that's wrong, that you must have some kind of assumption, some combination of assumptions and some variation in the data in order to draw inference. And that's really been a huge theme of this literature over many decades. So important takeaway is that if somebody tells you they've measured the impact of changing price, for example, you need to ask, well, how did you learn that? What in the data allowed you to learn the counterfactual effect of what if the prices had been different in the past? They have to be able to answer that question. And if not, then you should be very, very skeptical of the results.